Hello everyone, my name is Randall Pike. This is lecture 5.1, Determinants in Terms of Cofactors. Now, so we have this new term now called the determinant, and it is a function that acts on matrices. So let me write it out here. So determinant is a function from square matrices, so n by n matrices, to the real numbers. All right, so it's a function. So we'll usually write it as det. So there's the input is a matrix A, and the output would be a real number. So the domain is square matrices, n by n square matrices. So there's actually one function for each such size of matrices. So there's one determinant function for the 2 by 2 matrices, one for the 3 by 3 matrices, etc. The codomain is the real numbers, but actually the range is the real numbers. So that means the determinant function can assume all possible real numbers. Okay. Now, if you think about an n by n matrix, it has n squared entries. Okay, so that's a lot of numbers when n is large. If n was 10, that'd be 100 numbers. And these entries are working together to determine the features of this matrix, the way it acts on vectors, for instance. And whether it has an inverse also is another important property that these numbers determine. Now look at this determinant function. It's taking n squared numbers from the entries of an n by n matrix and converting them into a single real number. So on the surface, it might think that this determinant function can't really tell us too much about a matrix because it's taking something that has many entries possibly, and many variables in terms of the entries, into a single number and trying to characterize those matrices, all their numbers, how they work together by a single number. But by the way we define this, and you'll see below that definition, it is rather involved definition that involves takes into account all the entries of the matrix. That particular formula that we'll see does in fact give us a lot of information about the matrix, okay, as we will see as we work through these examples. So let's begin with our definition of the determinant, and then we'll do some examples. So to begin with, I could write right here, okay, that's a 2 by 2 matrix. So let's write out determinant of a 1 by 1 matrix. There you go. So there's a 1 by 1 matrix. Maybe I'll just write it as A, okay? So matrix A equals A, where A is just the matrix with the single entry A. All right, so there you go, for 1 by 1 matrix. Now let's move on to 2 by 2 matrices. And here it is here. So there's an arbitrary 2 by 2 matrix, and this is the formula for the determinant. Okay, now there's two things in here. There's the function determinant with its argument A being the matrix. And now this notation here, okay? Notation. Now, this is not absolute value, so don't get confused. It looks like that. It's two vertical lines, but it's not. It does not mean the absolute value. All right. So that's something you'll have to be aware of. We can also write this as bar A. Okay, so that's another notation for determinant. Okay, this one here. So I can put the two bars around the matrix A, vertical lines. It looks like absolute value, but it's not. If you know that the inside is a matrix, then you interpret that as determinant. And remember, the determinant up here, I'll remind you again, can be any real number, positive and negative. Okay, so don't interpret that as an absolute value. And just to make it more clear, thus, You may see this sometimes. So there's a big absolute value sign. There's two smaller ones around a matrix, okay? Thus, this means the absolute value of the determinant. Okay, so there. So it means the absolute value of the determinant. Okay, so new notation for you, and as you know, mathematics uses a lot of notation to incorporate all the ideas. Okay, now that's the formula for it right here. This is your formula for the determinant of a 2 by 2 matrix. Notice it's a product of pairs of numbers in the matrix and a sum. In this case, it's a difference. All right, and that's what we'll see below, is that when you're computing the determinant of a matrix, you're taking products of entries and then you're adding up these various products, okay, with minus signs thrown in at the right place. Okay, so just to illustrate this formula here, let's do one example. So let's take a 2 by 2 matrix. So A is equal to, let's say 2 minus 3, 2 and 4. All right. So following that formula there, okay, so absolute or determinant of A is, so it's the top left entry times the bottom right entry. So it's going to be 2 times 4 minus, and then the other anti-diagonal entries, their product. It doesn't matter which order you write the product. So I may write it differently at different times. It doesn't matter because this multiplication of numbers is commutative. So I'll just write it down. I'll write it down as it's written here. So it's minus 3 and then 2. Okay. So now we have, good. So this is now going to be 8 plus 6 is 14. Okay, so we'd say that the determinant of this matrix here is 14. All right. Now, let's go on to something bigger now. So this definition of determinant in terms of a 2 by 2 matrix is enough for us to define the determinant for an arbitrarily sized matrix now. Okay, so let's move on to the 3 by 3 matrix. That's all we'll talk about in this section. There will be analogous formulas for n by n matrices. Actually, we'll see that abstract formula down below. But because, as you'll see here, the formula is getting more involved as we get larger and larger, we'll introduce some notation to simplify it. So the formula for a 3 by 3 matrix is as follows, and here we're the fundamental feature of the determinant function is that it's defined recursively. So now you'll see that the 3 by 3 determinant of a matrix of a 3 by 3 size will be written in terms of determinants of 2 by 2 matrices. All right. So here's one definition of the determinant of this matrix A, and I say that the term it's one definition because there's many equivalent ways to write out a determinant, as we'll see below. So here's one. So it's A11. Now I'm going to use the symbol for determinant here. Now I'm going to write down a 2 by 2 matrix that's composed of entries from this 3 by 3 matrix. So it's going to be A22, A23, A32, A33. All right, so that's a 2 by 2 matrix, and you can see it's coming from the entries of this matrix A. That's one term in the determinant. And then I have a minus A12. Okay, so A11 and A12 are those entries in the top row. And I have these smaller 2 by 2 matrices. This one associated to A12 is the submatrix A21, A23, A31, A33, and one more term. So I'm going, you see I'm taking the entries in the top row of A is A13 times this submatrix now, A21, A22, A31, and A32. Okay, so now that's the formula for a 3 by 3 matrix. So notice it's defined in terms of 2 by 2 matrices. Determinants of and these will refer to as sub-matrices of A. Okay, so they're smaller matrices than A, but they're composed of the entries of A. Now, if you look at this, these 2 by 2 matrices closely, you'll see that the ordering of the entries is the same as the ordering they appear in the matrix A. We're just not writing all the terms down. Okay, so it's important to keep that in mind. We're not rearranging the order of the AIJ entries. We're just selecting 4 of them in the appropriate way. Okay, so that's one formula. One formula. And I'll say this here. See below for the general formula, for the general definition of the determinant. Okay, so this is like a particular definition. All right. Good. So we can do one example here. Example. So let's take, I'm just going to write here, let's compute the determinant of this matrix. 2 minus 2, 3, minus 1, 1, minus 2, 0, 1, 1. Okay. See what I need to do here. Give myself some more room. Okay, so let's go. So I'm going to follow the formula above, which if you look at it closely, it's the entries in the top row are appearing alongside the determinants of these 2 by 2 submatrices. Now, the first term, let me just highlight it here. Okay, so I'm going to concentrate on that 2 there. So that's the A11 term. So it's 2 times. Now, the 2 by 2 submatrix is the following. I'm just going to do this in yellow, then I'm going to remove it. So I'm concentrating on that A11 entry, which is 2, and I've highlighted it there. And then what I do is in my mind's eye, I remove that column and that row. Okay, so the column and row where the entry I'm choosing, I remove those columns and rows, and that determines the remaining 4 entries, which is the 2 by 2 submatrix. All right, so that's how I obtain that submatrix. Minus 1, minus 2, first row, 1, 1, second row, is because I'm concentrating on the 1, 1 entry in the original matrix A, and in my mind's eye, I delete that row and that column, its row and its column. The entries that remain in the big matrix A is my submatrix. All right, so I've done that. Now I'm going to remove those highlights. Actually, I shouldn't write like that. Maybe I'll just delete them in a more simple way, like this one. Okay, so let me get away. Good. So now let's start again. Now I'm moving across to the next term. Now notice the next term has a negative sign attached to it. So it's negative 2 times. Now what's its 2 by 2 submatrix associated with this entry 2 now? Okay, so in my mind's eye, once again, I remove its row and its column. There we go. And I see the submatrix that's left over. It's minus 1, 0 in the first column, and minus 2, 1 in the second column. Okay, so that's how I obtain the 2 by 2 submatrix for this entry. Okay, now following the formula above, I'm on to the A13 term now. And that term here is 3. Okay, so it comes with a plus sign, plus 3. Notice in this formula up here, I'll highlight the entries A11, A12, A13. I'm not suggesting that these are positive or negative numbers. They're just numbers that appear in the matrix. But it is very important to know that there's a minus sign here and there's a plus sign there. Okay, that's important. That's part of the definition. So you add those, the negative signs separately when you're writing out this formula. So let's move on. So now I'm looking at that third entry, and I'll just highlight it here. Okay, there it is. So I'm looking at this entry now, and so in my mind's eye, I remove the row it's in and the column it's in, and that reveals the 2 by 2 matrix that I write here, whose determinant I will need to compute. There it is. Good. Good. So I followed the formula above, and I've written out the determinant of this 3 by 3 matrix. And notice it uses 3 2 by 2 matrices. Now, to compute the 2 by 2 matrices, those determinants, I have to go back to this formula. Now, this formula is pretty easy to remember. There's a pattern. Okay, so let me just write it right here a little bit bigger. A11, A12, A21, A22. Okay, so there's my matrix. So let me just write it that way. And then yellow, I'll show you it's this product minus this product. Okay, so there's my minus sign there. Right, so it's the diagonal. So I have these arrows, one going down and one going up. So the downward one is the term on the left and the upward one is the term on the right, and it comes with a minus sign, the second term. So that's the kind of pattern I'm looking at in these examples here. So let's continue them. So this is going to be 2. Now I compute this determinant. So it's this product minus this product. Okay, so it's 1 minus minus 2, which is a 3. Okay, so let's do that. Then I'll move on to the second term. So it's minus, minus, actually I wrote that. Okay, that's fine. So minus 2 times, you know what, in my notes I have an extra minus sign in there, and I think that's probably important. So let's do it that way. So I'm going to put a minus sign here. This is what I meant. Okay, so minus sign here. So that's why I just want to emphasize this, because this will bring to light how these additional minus signs are coming in. So there. So that the second entry in the top row is a -2, but I still have this minus sign on the outside. That's part of the definition. Okay. So let's work with that matrix. That doesn't change the sub-matrices that I've written down already. So let's continue on. So now I'm moving across here. So it's minus minus 2. Now let's compute that determinant of this 2 by 2 matrix. So I see that it's minus 1 times 1. So it's minus 1. And then the other product going upwards has a 0 in it, so it doesn't contribute. So it's just minus 1. There's my minus 1. And then on to the third term, which is 3. Now this matrix, this 2 by 2 matrix, is that product minus this product. And once again, it has a 0 in the second product. So it's just the first product, which is again minus 1. Okay, now I'm ready to do that multiplication. So 6, and then there's 2 minus signs. So that's minus 2. Yep, so minus 2, and then minus 3. So this 3 by 3 matrix has determinant 1. Okay, so that's this example of a 3 by 3 determinant. So as you can imagine, for larger and larger matrices, if we were going on to a 4 by 4 matrix, I'll do one below, its formula would be reduced to a sum of 3 by 3 determinants. And each one of those I'd have to do this way, reduce them to 2 by 2 determinants. So there could be a lot of computation involved in computing determinants of large matrices. Okay, but they all boil down to this stage here when you're at the 2 by 2 stage, and you simply use this formula that was given to us up here. Okay, so we'll see that in action as we go down the list here. And this is going to aid us in expressing this more general formula. So some definitions here, cofactors and minors. Okay, so there's a matrix with entries Aij. So let's define the minor entry associated to Aij. So the minor entry is associated to a specific entry in the matrix. So you can think of this minor matrix, minor of Aij, as coming with a index itself, and there it is. Okay, so you see the minor of the entry Aij is denoted by capital M sub ij. So the ij is associated to the location in the matrix of A whose entry you're examining. Okay, so there's a minor there. Now this minor is itself a determinant of a submatrix. Okay, and that's what we were doing above. So it's a determinant of a submatrix, this Mij. So the Mij is going to be a little bit of work to compute. And as I suggested above, it's obtained by removing the ith row in the jth column of A. And that's what I did above here when I was considering an entry in the matrix. Here it is up here. I would, in my mind's eye, maybe I'll just draw one in here. So if I was looking at A22, so this is, sorry, A12, okay. There's my A12. Then I remove the first row and second column, and I'm left with this submatrix here, okay, which is over here. So this is the minor M12, okay. So from little a12, the entry in the 1, 2 position of the matrix, I have the minor capital M12, which is the determinant of the submatrix you see inside the matrix A once you've removed the row and column that A12 is sitting in. All right, so that's what that definition is referring to here. So the little aij and the big Mij. Now, when you're computing Mij, it is a matrix. Remember, it's it's the determinant of a submatrix. So you'll have to sit down and work out its determinant first. And then the cofactor, you put those two together. Cofactor associated with that entry, so that's why it comes with a sub ij, because it's associated with that entry, is this term Mij, which is the determinant of that submatrix, and then this other factor, a plus or minus 1. So this term right here is a plus or minus 1. And that's why you'll see me putting down minus signs occasionally in the formula of a determinant. This is how I'm computing where I put in a minus sign. Okay, so that's the cofactor. So let's do an example with a large matrix. Actually, that one above. So let me write it out again here. So example, A is 2, minus 2, 3, minus 1, 1, minus 2, 0, 1, 1. So that's the matrix I had above. So let's just write out what these minors are. So remember, the minor is it's a determinant of a submatrix, so it's a number. Okay, so, and it's obtained by taking the determinant of some smaller matrix. Now, the size of the matrix you're using to compute the minor is one less the size of the matrix A, because you've obtained that submatrix by removing one column and one row. So it's one less size in terms of rows and columns as A is. So here A is 3 by 3. So its submatrices would be 2 by 2. Maybe I'll make a little note here. Okay, so right here. So if A is n by n, this submatrix is size n minus 1 by n minus 1. Okay, so it's one less. Now, so here it's going to be a 2 by 2 matrix. So what I'm going to do is I'm going to remove the first row and second column. So I'm just doing it without drawing those lines, but you might want to keep those lines in there as you're working just to get used to it. So there's M12, okay? And now I'll go to a few entries. So let's take, sorry, M12, yeah, that's correct. Let's do something different. Let's do M23. Okay, so now M23 is going to be the determinant of the submatrix you obtain from A if you remove the second row and the third column. So maybe in this time I will write it out. So I'm going to remove the second row and the third column. Okay, so this is the A23 entry I'd be considering. It's the minor associated with that entry would be the 2 by 2 matrix I see there that's not covered by the yellow lines. So 2, minus 2, 0, 1. All right. So there they are. And we can compute these now. So this determinant is, I see it's minus 1. Okay, so notice once again, just in case, I've seen this before, students get confused that this is an absolute value, but yet it's producing a -1. It looks like an absolute value, right? But it's not, it's a determinant. So it can be any real number. In the second case, I have 2 times 1, it's simply 2. Okay, so there we go, M23. Good, now let's move on to the cofactors. So the cofactors, if you look at that formula, it's plus or minus Mij. Okay, maybe I'll just write that down here. So Cij is equal to plus or minus Mij. So once you've computed the Mij, you're basically done computing the cofactor. You just have to determine where the plus, where do I put in a minus sign? So let's do that here for these 2 entries. So C11, well, I'm going to start at the beginning. I'll start with C11. So C11 is going to be, according to my formula, -1, notice the exponent there, it's the sum of the indices, so it's 1 plus 1. Okay, so it's -1 to the power 1 plus 1, which is the power 2. Now this C11, the M11 is 3 here. You can, maybe I'll write that down here, M11 is 3, so I did that before. So this C11 is equal to M11, okay, because the term, the -1 to the power I plus j term just comes out to be 1. However, if I go to C12 now, you'll see something changes because now it's -1 to the power 1 plus 2, which is 3, which is odd. So that's going to give me a negative sign. Now C12 I computed above is -1. So here I get -1 times -1. I get 1. So C12 is not equal to M12 here. It's the negative of M12. C23 is going to be factor -1 to the 2 plus 3. Now that's 5, so it's again odd. Okay, so here once again, C23 is not the same as M23, it's the negative of it. So a -2. Okay, so that's some terminology, some notation that's going to assist us in writing down the general formula for the determinant of a matrix. So as you can see, these terms are built up of determinants of smaller matrices, and also these maybe at the moment enigmatic factors of plus or minus 1. Okay, all right. So and that's illustrated in this theorem here. Okay, so this is a theorem that's telling us how we may compute the determinant of an arbitrary n by n matrix. Now notice this notation. A is denoted by, so there's my matrix capital A, but we can also write this, it's customary to do this with square brackets around a smaller aij to denote that it's a matrix with aij entries, and n by n denoting the size of it. Okay, so what does this formula say? This is the definition about using cofactor expansions. Cofactor expansions, these are the cofactors. We've just defined it. They're right here. All right, so it's given in terms of these Cij's. Okay, so our determinant function is going to be written out in terms of these Cij's. Now notice the Cij's, there's n, there's 2n such. Sorry, that's not right. There's n squared, right? I just want to point out there's many of these Cij's. So there's one for each entry. So there's n squared such cofactors. So if you think of these Cij's, remember they're numbers, and with their subindex ij here, they actually form a matrix of the same size as A. It's actually called the adjoint, which we won't pursue. But you're computing as there's as many cofactors associated to a matrix as there are entries in a matrix. So there's a lot of cofactors, n squared, and each one of them has some effort to compute. Luckily, we don't have to compute all of them, and that's one of the aspects of this theorem here. Only a select few of the cofactors are involved in computing the determinant. But the remarkable thing is, and that's illustrated here in these 2 sentences, is that there's a variety of ways of which we can select those cofactors to compute the determinant, and they all give the same answer. As long as you stick to this recipe in front of us, the determinant will be uniquely defined no matter which way you do it, okay? So here we go. So now notice, so that's what we mean by cofactor expansion. We mean we're computing a determinant by expressing it as in terms of some of the cofactors, okay? Now, which cofactors are there? Well, here's two selections, okay? You can go along the jth column or along the row, all right? So you have row options to compute the determinant or columns. You can select either one, and they give you the same answer, which is a long story we don't get into here, right? Same answers, all right? No matter which way you do it. Now, read this formula carefully. It's all here. What do we recognize? We recognize the cofactors. So there they are, okay? So let me put the cofactors in blue. Now, before I continue on with the formula, notice the sub-indices here. So I'm talking about this one right here, the cofactor along the jth column. Notice the j is occurring in every term here in this sum, and it's not changing. So the j is the same, and that's the second entry when we have this notation is the column. So if you look at these numbers appearing here, the aij's, I see a1j, I see a2j, etc. I see out to anj. So in other words, I see the jth column here. So a, n, j, okay? So the jth, that's the jth column entries. Hence the name expansion along or down the jth column. All right, that's what I see there. Whereas down here, if I look closely at the indices, I see a, I. Notice now along the ith row, all these indices have an I in them, okay? And the first component, and it's fixed. Notice the indices in both of these, they're the same in the cofactor as they are in the entry. So A12, C12, etc. And the i's are always the same in all these entries, but it's the second components that's changing. So I see AI1, I see AI2, all the way down to AIN. And when I ask you what are those entries, you recognize that to be the ith row entries in A. So that's the ith row entries. Hence the name expansion across the ith row. Okay, because it only takes into account the entries of A in the ith row, whereas the previous example, cofactor expansion along the jth column, only uses the entries from A in the jth column. Now notice also here you have n choices, because it's not telling you which one of the rows or columns to use, n choices for row, and you have n choices for column. Okay. And so you have how many options? You have 2n ways to compute the determinant. All right, so that's a lot of choice to do. All of them give you the same answer. That's one of the keys in this theorem, is that all these formula, there's 2n different formula here. They all give you the same number, which is the determinant. That's why we call that the determinant. There's only one determinant of a matrix, but there's many ways to compute it. That's the interesting feature about the determinant function. Okay, so let's do an example of a larger matrix, and I'll compute it several ways, and you will see the answer coming out the same. All right, and that's a theorem that the answer is the same. So here's a 3 by 3 matrix. Now, good. So they're asking us to do it along the first row and then the third column. All right. Now, typically, you would be doing this yourself, which row or column to select for computing the determinant. And I'll give you a little hint here of what might cause you to select one row or one column over another, is that if you go back to this formula here, right, notice the expansions across columns or rows. they're a product of the entry and the cofactor. All right. Now, if the entry happens to be 0 there, then that means not only is the sum there shorter, but you won't have to compute the associated cofactor. Right. So for a 0 entry in A, the associated cofactor would not have to be computed because it would not appear in this formula because it's a 0 times it. Right? And remember, cofactors are actually where all the work is when you're computing determinants, because they themselves are determinants. Okay, so here, I just want to make a note. Note the 0 entry. At A33. All right, so that means if I wanted to compute determinant, it may make sense, because it's so computationally intensive, to select either the third row or third column. They didn't ask us to do that. They asked us the third column. So select third column or third row. Okay. Now I'll do something maybe a bit naive. I'll do the first row and then the third column. How's that? Okay. But that's one of the consequences of having all these formulas available to you, is you can select which one to use in a given situation. If your matrix has no 0 entries, then well, it may or may not matter which way you do it. So let's show that this formula, the definition above, does give us the same answer. So the first row, I'm going to go across the first row, expansion across the first row. So just one more look at that formula. Okay. When you go across a row or column, it's a product of the cofactors and the entries in the column. Remember, the cofactors are two components. One is the determinant of a submatrix, and the second factor is a plus or minus term that we compute -1 to the exponent I plus j. All right, so I'm going to do all that at once. So going across the first row, I see my first entry is -2. Now I plug in the plus or minus 1 factor. So this is the A11 term, so A1 plus 1. And then I have my Mij. So in my mind's eye, I remove the top. I'll do it in yellow here, then I'll erase it. I remove that row and that column, and that leaves me with a 1, a 4, a -8, and a 0. Okay, so let me get rid of those lines again. Then I move across. So +3 now, and now I put in this term -1 to the, and now I'm at the 1 plus 2 entry, the 1, 2 entry. All right, so I can see that's an odd power, so it's going to give me a minus sign. And now I look at the minor associated to the entry A12. So once again, in my mind's eye, I'll just remove its row and its column, and I'll see what matrix remains there. 5, 4, 4, 0. All right. Move those away, and I'll move on to the next term, which is a 1 with a -1. Now this is the 1 plus 3 entry because I'm at 1, 3, and the sub matrix I see there, so I'll remove that first row in that last column, and I see it's a 5, a 4, a 1, and a -8. Good. All right. So I've applied the formula above, the second formula here, okay, the second one, cofactor expansion across the ith row, and I selected the third row, so I is 3 in this case. Sorry, first row, so I is 1 in this case, yeah. And then I've written out the cofactors, and I've put in the plus or minus sign as appropriate. So here it's -2 times, okay, and I see what? -32 here. Sorry, yeah, 4 times -8 is -32, but remember the determinant, that's coming with a negative sign, so it's 32. And now I get a minus sign coming from that factor -1, so it's -3, and now the M12 entry is going to be -16. All right, and then I get a plus sign here, and I have a factor 1. And then the M13 term is the determinant of that submatrix, which looks like it's -44. Okay, you can confirm. So it's 5 times -8, so -40 -4, so -44. And that turns out to be 60. All right, so that's our computation of the determinant of A using expansion across the first row. Fine. So now let's go to third column, which will be a little shorter because there's a 0 there. So I'll only have 2 terms in this expansion. So here we go, third column. So I can tell you I'm computing the determinant. So I'm at the top of the third column. So there's my 1. And then I put in that term -1. So I'm at the 1, 3 entry, 1 plus 3. And now I've just finished computing this submatrix. So there it is. Okay, and then I'll move to the next term in that column, which is 4, but it comes with a -1 factor to the, now I'm in the 2, 3 entry. So second row, third column. It's a 4. And that submatrix now, I'll just draw it here, all right, is -2, 3, 4, -8. Okay, now you see the next term in that column, the bottom entry A33 is a 0, so I don't have to write the third term in, and therefore I don't have to compute the minor entry M33 because there's a 0 coefficient in front of it. So I'm done computing using the formula for the column expansion. Now let's just do the computation. So I get, there's a -1, sorry, this is, yeah, so the -1 factor comes out to be 1 because it's power 4. So it's just 1 times this determinant, which is -44. I've done that before. And now I get a negative sign here coming from the -1 to the power 5. And the minor is also negative. Sorry, is it negative? The minor is, sorry, just 4, right? So 16 minus 12. Okay, so it's 4. So -4 times 4. Okay, so I get -60. Actually, that's a -60 up here. Sorry, this is a -60. Now I realize it. A -60. Okay, as it should be. They should be the same. So that's one computation of the determinant of A, and there's another computation of the determinant of A. So I'd say for exercise, I'd say compute, just to get used to this, compute det A along other rows and columns, okay? So you should always get this number -60, just for practice, because you know what the answer is. All right, so there we go. I'm going to do a 4x4 matrix below here, okay? So let's talk about this question here. The determinant of a matrix with a 0 row. Well, remember from the discussion above, the selection, that is this theorem, the selection, the row or column you select to compute the determinant of a matrix is up to you. They all give the same answer. So you make a judicious choice about which column and row to make your calculations as quick and simple as possible. I applied that here when I did the expansion down the third column or the third row. Both of them would only have 2 terms in it because one of the entries in that row and column is 0. If you go here, if you have a matrix with a 0 row or a 0 column, okay, then we expand across that row or column, okay, that row or column. So I'll use the theorem for computing determinants, and I'll choose that row or that column, the one that's all zeros. Okay, when I do that column, the Aij appearing in that formula are all 0, and hence when I compute the determinant using those formulas, I'll get 0. Okay, so in particular, the 0 matrix has 0 determinant, but many other matrices have 0 determinant. You know, I can write down a rather large matrix with lots of big numbers, like this 4x4 matrix. Okay, but if one of the rows happens to be 0, okay, so here's a row of zeros, okay, so I can see right now, so let's call this matrix B. I can see that in the matrix B has determinant 0. Now imagine the amount of work that would be involved if you were doing expansion across a different row or column. With these large numbers, you're going to get very large determinants, minors coming out of the formula. So it's going to be rather cumbersome algebra. But in the end, it will turn out to be 0 because I can see right here that expansion across this third row gives me 0. So this matrix has determinant 0 any way you do it. Okay, so make a wise choice. Another thing we can get, so this is an easy computation. So some matrices would be easy to compute the determinants if it's something obvious like this. Okay. Now there's more subtle, I won't go into it here, but also determinant equals 0 if one row or column is a linear combination of the others. All right, so that's a little bit more subtle because, as you know, it's not so obvious to tell if one vector is a linear combination of the others. But if that's true, then the determinant is 0. Okay, so that's another feature. If you knew that fact, then you could immediately say the determinant is 0. And the reason I say that here is because this statement uses this exact statement up here, that if there's a 0 row or column, the determinant is 0. Because you think about this. If a row or column is a linear combination of the others, you can make that row 0 by using that linear combination. So you can create a 0 row out of it. And then from that, it follows that the determinant is 0. There's a little bit of subtlety still involved here. Maybe I'll write this out for reference. You can make that row or column 0, column 0 by row operations. Okay, plus the fact, all right, that this row operation, adding a multiple of one row or column to another, so you can do column operations in the same sense, doesn't change the matrix. Okay, that's a fact. It's not obvious, and it's actually quite miraculous, but it's true. It doesn't change the determinant. So the determinant of the matrix you obtain by those row operations, adding multiples of one row to another or one column to another, doesn't change the determinant of a matrix. It changes the matrix, but not the determinant. All right. So in the case where you have a row or a column that's a linear combination of the others, then through these kinds of row operations, adding multiples of other rows to it, you can create a 0 row, and therefore at that stage you immediately see that the determinant is 0. So that's the reason this other fact holds, that if a row or a column is a linear combination of the others, then the determinant of that matrix will be 0. And this is used actually to show whether columns or rows are linearly independent. Okay, so it's another way to do that kind of problem. We're not going to spend much time working on these subtleties, but that is another feature of how the determinant is used. Okay, on to another example, another situation where you can see pretty quickly what the determinant is are the triangular matrices. So I'll just write down all the three types of matrices I'm talking about. So the upper triangular, okay, so that's when the non-zero entries are in the upper triangle part, upper part of the matrix, and then the lower triangular. I'll just do an example for one of these forms. Okay, so the lower triangular has the matrices, the non-zero entries in the lower part, triangular, and then the matrix that is both, the types of matrices that are both upper and lower are the diagonal. All right. All right, so a diagonal matrix is both upper and lower triangular. All right, so this is what we're talking about. And I'll just do one example and then I'll state the result, and you'll believe the result once I do this calculation. So I'll write down a 4x4 upper triangular matrix. Okay, so 0 minus. So all I have to do is make sure that the non-zero entries are on the diagonal or above. Okay, that's all. So this matrix here is being produced. Okay, here we go. So there's an upper triangular matrix, 0 entries below the diagonal. All right, now once again, make a judicious choice about how you're going to compute the determinant of this matrix. Well, look at the first column or the fourth row. That would be a very good choice to do your expansion because there's only one non-zero entry. Okay, so you're alleviated of the task of computing those three minors for those other terms. Okay, there's only one minor that needs to be computed. It doesn't mean it's going to be that easy because when I do the expansion across any row or column here, remember the submatrices are going to be one less the size of A. They're going to be 3x3 matrices. Now a 3x3 matrix could take some time to compute the determinant of, as we've seen above. Okay, so don't get your hopes up too high yet, but we'll see it works out very nicely here because if I choose the first row or the third column here, which is an obvious selection, so I'll just highlight them. So I'll either that column or this row. It may not be obvious right now, but if you think for a little while, you'll notice that the minors for all these entries will also be upper triangulars. So we'll have this very nice, efficient way to compute determinants if I stick to this either first column or fourth row here. So I'm going to do the first column expansion. So expansion, and maybe you should try the fourth row yourself to see it comes out the same. So expansion down first column. All right, so determinant of A is, so there's my 2. Now I'll put in the -1 factor, but it's the 1, 1 entry, so I know that comes out with a +1, but I'll just write it here. And now the all important, so remember this expansion down the first column, or the same with the fourth row, there's only one entry in the expansion, and I'm writing it out here. So now I write the minor, so I remove the first row and the first column here, and I see what submatrix results. So it's 3, 1, 2. So it's a 3x3 matrix. Oh, sorry, it's not that, right? That's the row that's gone. So I'm down to -1, 4, 3. All right, and then 0, 7, 4, and then 0, 0, 3. All right, now here's the interesting feature. It's also upper triangular. Okay, so what that means is it itself, this minor I have to compute, is also pretty easy to compute. Okay, so let's go. So I'm going to continue on with this. So it's equal to, so far I have a 2 here. Okay, and then I have, I'm going to expand across the first row again. I mean, across the first row. Am I going? Yeah. Or the first, I'm going down the first column again, okay? So, yeah, so down the first column, I'll have a -1 entry. Now notice this -1, its minor term has a plus factor because this is a 3x3 matrix, and I'm considering this -1. Maybe I'll write it here in the 1 + 1 entry. So it's no longer the you can see on the matrix A to begin with, that's the -1 here, okay? I'm not thinking of it as the entry in the matrix A. I'm thinking of it as the entry in the submatrix, all right? So it's the 1, 1 entry in the submatrix, so that's why I won't pick up a minus sign there. And the submatrix associated with that entry is this one, 7403. Okay, so now once you reach the 2 by 2 stage, you can stop and then use the formula for 2 by 2 matrix. So combining these all together, I see I have this 2 here, I have the -1, and then now I'm computing this determinant, but I'm writing it all out as factors just to illustrate that it's the product of the diagonal entries in the triangular matrix. All right, so that's the important result we want to observe, product of diagonal entries. All right, so that's the answer for this kind of the determinant of these kind of matrices. Their determinants are easy to see, easy to compute. You just simply take the product of the diagonal entries, and the reason for the determinant being the product of the diagonal entries is this way of computing it. You select either the top row or the first column to do your expansion, and you keep selecting that first row or column in your submatrices, and you have so many zeros in your submatrices that you only end up taking products of the diagonal entries. Okay, so that's the two obvious types of matrices whose determinants are easy to compute. These ones that have 0 rows or 0 columns, and these triangular ones. And then the more subtle one is these ones that have rows or columns that are linear combinations of the others. Okay, so let's try a non-obvious, a 4 by 4 matrix that has no special features, although this one has a lot of zeros in it, I can see. So here, I'll just make a note here, make note of a lot of zero, or maybe I'll just write that there's a lot of zeros here. Note there are many zeros. So you want to take advantage of that. There are many zeros. All right, so you want to choose a row. I'm going to do an expansion across a row or down a column that has many zeros. And I'm looking at this matrix here, and I notice the second column has 3 zeros, and that beats all the other rows or columns. There's other rows and columns that have 2 zeros, but this one has 3 zeros. Okay, so why not do expansion down the second column? So expand down the second column, just to give us a shortcut initially anyways. Notice that it's more tricky to see what's going to happen at the next stage when you're computing the 3 by 3 determinants of those submatrices. You have to, it's not clear how many zeros are going to be resulting there, because I'm eliminating a lot of the zeros when I eliminate that second column and first row. But anyways, you do what looks best initially, and what looks best initially is expansion down the second column. So expand down second column. Okay, let's go. So I go, well, there's a 0 in the first entry, so I'm down to the second entry in that column, so it's 1 times what's the determinant of submatrix. When I remove that row in that column, I get 1, 4 minus 2, 0, 0, 7, 3, 1, 1. All right. Sorry. Yeah, 3, 1, 1. So I'm drawing these. I should remove that one. It's not this one. It's this one right here. So yeah. So that's where I'm at that 1, 2 entry, and that's the I just eliminated that second row and second column. So this is the submatrix, the 3 by 3 submatrix I see left. Okay, so that's the only term in the expansion down the second column. Okay. And now, because there's lots of zeros here, I'll also expand down the second column. All right, so I'm going to expand down that column. So I get my -1. Now I'll compute the 3 by 3 determinant. So going down the second column, I'm at the term 7. Now notice 7 occurs, so there's my plus or minus 1 factor. That's 7 at the bottom. There's in the 3, 2 entry, 3 plus 2. Okay, 7. And then the 2 by 2 matrix I get by eliminating that bottom row and middle column is 1, 4, 3, 1. Okay. Good. So now I get my minus 1. Sorry, where'd that minus 1 come from? It's not there's no minus there, right? That's the 1 from the previous step. So I'll leave that out. So I do get a minus 1 factor times the 7, and then I compute that 2 by 2 determinant, which is 1 minus 12, so it's minus 11. And so that gives me 77. Okay. So you can check expansions across other rows or down other columns, and you'll get the number 77. But this selection of the second column to do the expansion just helps us, initially at least, reduce the number of computations. Okay, so that's a judicious choice of which column or row to expand across. Now here's an interesting feature that might be might be pretty obvious to you, because because we can compute determinants through row or column expansions. The determinant of the transpose is the same as the determinant of the matrix. Okay, so that's this statement right here. So remember, A and AT are both n by n matrices, but AT is a completely different matrix, although it has the same determinant. And that's not hard to believe, perhaps, because when you compute the, for example, determinant of A by expanding across the row, then that row can be thought of as a column of AT, and you can expand down that column. So it seems like you should get the same answer by just either computing row across the row of A or down a column of AT, because the resulting matrices computations would be the same. Let's see how that works in practice. Let's take an A that's 2 minus 2, 3. So a 3 by 3 matrix. All right, and AT, the transpose, as we know, is we reflect the rows into columns. So minus 1, 1, minus 2, 0, 1, 1. Okay, so that's A and that's AT. So this is what I was discussing before, but maybe we should start up here. So let's take let's look at why it's true for the 2 by 2 matrix. Then I won't have to write all that out down here. So 2, 1, A2, 2. So remember, for a 2 by 2 matrix, this determinant was defined to be A11 times A22 minus A21, A12, and that is the same as the determinant of this 2 by 2 matrix transposed. Okay, so if I write out the transpose of this 2 by 2 matrix, it's A11, A12, A21, A22. All right. So that's the definition we stated for the determinant of a 2 by 2 matrix, and you can see that in the case of 2 by 2 matrix, it's the same number you get by applying that formula to the transpose of the matrix. Okay, it's the same number. But this is true for any size matrix. The determinant of the transpose will be the same as the determinant. Let's illustrate this here. So I'm just going to, for this one, I'll just pick an arbitrary row to expand across. I'm going to expand across the first column. Okay, or sorry, I'm going to expand across the second column of A. So let's write it out here. So determinant of A will be, so I'm going to leave out those factors of plus or minus 1. I'm just going to put them in when I see that there is a factor of minus 1. So here, going across the second row, that's the 2, 1 entry. I do get a factor of minus 1. So there's actually 2 minus 1s there, one coming from the entry and one coming from the minus 1 to the ij. And then the submatrix is going to be here when I eliminate the first column and second row. It's this one here. All right. Then I move across to the 2, 2 entry. So that term comes with a -1 to the 1 plus 1, or 2 plus 2, so it gives me a plus sign. So no change of sign there. So there's the entry 1, and then the submatrix is going to be 2, 0, 3, 1. And then go across to the -2 entry, which is the 2, 3 entry, but now the -1, I have -1 to the power 2 plus 3, which gives me a -1. So I'm going to get a minus factor there, -1 factor, times -2, and now the determinant of that submatrix is going to be 2, 0, -2, and 1. Okay. Whereas if I compute now I'm going to compute the determinant of AT by selecting the, so this was across second row. Okay. Now I'm going to go down the second column of AT. And that's where the row of A becomes the column in T. So second column. Let's see what happens. All right. So I'm going to go down the second column now. And I get, so starting at -1. Now that's in the 1, 2 entry. So I see I get a -1 factor from that -1 to the power ij. And now the matrix I get here, the 2 by 2 matrix I get here by eliminating that first row and middle column is -2, 3, 1, 1. Okay. And then I'll move down to the next entry, which is 1. And it comes with a plus sign coming from the -1 to the ij, power ij term. And its submatrix is 2, 0, 3, 1. And then finally, I'm at the bottom of the second column. So I do pick up a -1 term there. There's the entry in the 3, 2 position of my matrix. And the submatrix is 2, 0, -2, 1. Okay, so once I've made a selection of how I'm going to compute the determinant of A using any row or column, then when I go to compute the determinant of AT, I'll make sure I choose the appropriate row or column so that I have the same computation as I did for A. Now, if you look at these two formulas, the terms in front of the minors are the same, all right, because I'm going down the same, I'm going across the same entries in that row or column. And the matrices, the 2 by 2 matrices I see there now are the transposes of each other. But the 2 by 2 matrix, when you transpose it, you don't change the determinant. So we see here that the determinant of A transpose computed this way is giving me the same answer as the determinant of A. Okay, so this is illustrating this feature that the determinant of the transpose is the same as the determinant of the matrix. And it starts with an observation that when you transpose a 2 by 2 matrix, you don't change the determinant. And therefore, when you go to 3 by 3 matrices, by making the appropriate choice of which column and row you want to expand across, when you're computing the determinant, you see that you'll get the same answer. And if we went to the 4 by 4 case, I would do the same thing, because now I know that for 3 by 3 matrices, the determinant of the transpose is the same as the determinant of the matrix. So when I did the 4 by 4 case, my submatrices would be 3 by 3 determinants, and those matrices would be the transposes of ones from the other approach to computing the determinant of A. So same kind of observation, same kind of calculation would show you that the determinants, if it's a 4 by 4 matrix, then the determinant doesn't change if you take the transpose. So it's true for all matrices, and that's an important feature for us. All right, so I'm done my lecture here. I will stop the recording, and I'll see